project we are going to dive into.
So first of all, we're going to cover what is optical cloaking. Optical cloaking is essentially, we're altering the properties of light or using those to our advantage to try and make an object visible. And so one way we do this is by altering the velocity of light in a given material such that the light bends around a certain region of space, and in that region of space is where we put the object we want to cloak in. So if we look at this image right here, we can see path lengths of light coming in. They are all bent by a changing index of refraction, which we'll cover later. And they come out the same side. So if you stand over here, you're just seeing this light coming through. You're not seeing anything reflect off the cloaked object itself. So the ideal optical cloak is invisible to the entire electromagnetic spectrum, which is very difficult to do. It can be used omnidirectionally, i.e. from any perspective. All polarizations and medium independence. So I was having a little joke here, like, oh, here's a perfect optical cloak, because nobody would be able to see it from wherever you are in the crowd. So these are all the background topics I'm going to cover before we dive into what some of the current state of optical cloaking is. So first up is metamaterials. Metamaterials are human-made materials that have properties that are unseen in nature. And electromagnetic metamaterials are what we would use for optical cloaking. They tend to use a lattice design of different cells that have specific traits, and the structure is actually more important than the material makeup. And so these are things that we don't find in nature, because in nature you don't really find anything that's perfectly able to bend light around a certain area. So we're going to cover a bit of scattering in light. So in order for us to see, a photon needs to be absorbed by our eyes. So I currently can't see the presentation. Well, I can't see that, but I can't see this presentation on this board unless I had something like a common example is a rear view mirror. We have rear view mirrors, so we can have light coming in from behind us, bounce off that, and we can see it. So then we have an idea of what's going on behind it. Scattering occurs when a photon's path is altered because it runs into something like a molecule. And the very common example of this is why the sky is blue. Light coming in from the sun, and the sun doesn't produce anything like a white light frequency. White light is made up of all the colors of the electromagnetic spectrum. It comes in and it starts scattering off of molecules in the atmosphere. And it turns out that the amount that a wavelength will scatter is inversely proportional to the fourth power of the wavelength, which in English means that the shorter the wavelength, the more it's going to scatter. So that's why the light we see is blue, because blue is a very short wavelength. The reason we don't see violet, because violet's shorter, is because our eyes are more sensitive to blue. So if the ground were a perfect absorber and we had no atmosphere, we would see darkness everywhere except before we face the sun. And so I have a little image there. That's from Apollo 8, a picture of the Earth seen from the moon. We don't see any blue sky because there's no atmosphere, so there's nothing for the light to scatter off. And if the Earth weren't there and the moon were a perfect absorber, we would see completely darkness because there's no light that's being scattered, bounced into our eyes. It's all being absorbed by something. Only if we turn towards the sun would we be able to see anything. And I have another infographic here of a green leaf. We can see that all the light is being absorbed except for green. Green is being reflected or scattered, and that's why we see leaves as green. Permeability and permittivity are two properties of materials that we can alter. Permittivity is a measure of a material's ability to store energy in the form of an electric field. You can see that over here, a dipole that is heavily, has a high permittivity is able to alter its form much more in a given electric field. And permeability is a measure of how far magnetic field lines will penetrate into a material. You can see that here's some magnetic field lines, and as the permeability increases, we see more magnetic field lines able to penetrate the material. And we can alter the values of these constants in different materials. And this affects the speed of light in that material, because the speed of light is equal to 1 over the square root of the product of permittivity and permeability. So the index of refraction, now that we talked about how we can alter the speed of light in a material, the index of refraction is a material property that denotes the speed of light in a given material. And a larger value means that light will travel slower through it. And a way to try and visualize this is in the bottom left. We have a wavelength going into a area with different index of refraction, and we see that in order for it to slow down, the wavelength actually also has to decrease. So we get a shorter wavelength inside that material, but the speed, and that kind of helps visualize, I guess, that the speed is decreasing, although the frequency stays the same. And because of this change in speed, the light beam gets deflected, so you can alter the path the light takes. So a very common example of this is in spearfishing or if you go bow fishing, something like that. If you're trying to look at this fish, the light reflecting off the fish is coming out of the water, and then it's refracting at a different angle. And since we don't see this, you don't see this refraction, you just see this image. So what your eye traces is the fish is actually here. So if you wanted to throw a spear at the fish, you'd actually have to aim a little bit lower, because that's where the fish actually is, as opposed to where you think it is. Next we have anisotropicity and isotropicity. An isotropic material means the property is the same in every direction, and anisotropic means the property change in different directions. A very common example is wood, because you can go with the grain or against the grain, you're going to have different strength properties there. And so for optical cloaking, we want anisotropic, because as mentioned before, if we change that index to refraction, we want it to be changing throughout the material. We don't want it to just be going in a straight line. We want it to be constantly changing so it bends around the object. And so that's how anisotropicity fits into this. Parallax is perceived change in position based on the viewer's relative location. And so as you can see here, based on where the viewer is, they will have a different perceived image. And a very common example of this is if you hold out your thumb at something, you cover something, and you cover one, and you close one eye, and then you switch to a different eye, you'll actually see, like here I have that camera there, it's covered by my thumb, but now that I do it, I have to actually adjust it because I have a different relative location. And this is actually incredibly important to optical cloaking, because you can imagine if I am trying to focus outgoing light towards someone, and we have this sort of convergence at a focal point, if that person then adjusts their position relative to that focal point, that illusion of invisibility is going to be lost, and we're going to have to readjust. And so, this is my last slide, I promise. Now I'm going to go into active versus passive cloaking. Active deals using cameras to view what's behind you and then transmit that image in front of you towards something you're trying to spoof. And if you look at the bottom left, that's from The Invisible Man, which is a horror movie. I haven't recommended seeing it. But you can see here that all these little cells on the suit are little cameras that are trying to display an image to try and fool whoever's watching it. And so that's active cloaking, and that's partially where parallax really comes in, because if I'm trying to focus all these cameras on a specific area, but then somebody over there is looking, I have a mismatch of what people are trying to see. Or if the person moves away or towards me, they get out of that focal point, and now I have light diverging towards them, and the image is also ruined. Passive cloaking needs no additional input. So active cloaking, I need like a camera to focus on something and constantly change its value. Passive cloaking, I don't need any additional input. We're just using a changing refractive index to bend light around it. So this is an actual picture, by the way, in the bottom right here. And so that is the main difference between active and passive cloaking.
Okay, so now how do we cloak something? And again, I want to reiterate, how can we make an object appear invisible, so not disappear? But light either has to transmit through or bend around the object. You can't make light bend. So you need a material that will interact with electromagnetic waves in such a way that they bend around the object. And you need a material with a refractive index, which is related to the space that it's in. So 3 ways we could do this are by transformation optics, metasurface cloak, and reconfigurable and intelligent cloaking. So the first one, transformation optics. You have to vary permeability and permittivity in a material to have a changing index of refraction that causes the light waves to bend around the object. And then you need a material that works for all polarizations and wavelengths and that causes no reflection and is omnidirectional. And then, but this is kind of hard to do to have a material that is anisotropic distribution of permeability and permittivity. And in order to make the cloak more feasible, there would need to be an allowance for some reflection and allow for variance in polarization. So in this image, we'll say like this one, we have an object, and inside the object there's an empty space, and the structure of the cloak needs to be created so the index of refraction again is constantly changing, so the light, when it comes in through this object cloak, it's constantly being reflected through or bending around the object, if that makes any sense. It's kind of hard, I'm no expert, so. And then this is another, carpet cloak is another example of transformation optics. So subversion of this is a carpet cloak when an object is laying on a reflector. The carpet cloak would essentially make any reflection of a light wave look as if the object is not there. This allows for permeability and permittivity to have more relaxed values. And for carpet cloaking, this is it's only mostly been tested in smaller objects because this is hard to do for bigger objects. So if you want to hide a ring or bumps. The second one is metasurface cloaking. So imagine an object covered by a metasurface material that has cells, individual cells that can control the face of the material in every direction. Such an object would disappear from view in a monochromatic plane wave if it was incident upon it. And again, mono 1, so the monochromatic wave has a single frequency. The unit cells can vary in material and shape depending on the frequency of light we want to conceal. Again, metamaterials are composed from one material composed of different properties and structure. So this metasurface cloak would be like skin tight. It's made of a super thin insulator, material speckled with gold rectangles, and that would absorb and radiant light waves in a way that our eyes can't recognize. And this material is less than a micrometer thick, a fraction of the size of a human cell, which is crazy. And yeah, it can be wrapped around objects like a skin. Lastly, reconfigurable intelligent cloak. So unit cells contain a capacitor. So like this would be a unit cell, capacitor right in the middle. To vary its capacitance using a known initial condition voltage called advised voltage and machine learning. The variable capacitors can change the reflection of response on the fly. But this is kind of hard to do because you need like extreme math equations, and so if you're trying to actively cloak something, the computer would have to be working extra fast to figure out those nodes. And yeah, the calculations are hefty and it has to be fast math, so it's just harder to implement.
Alright, so now we have 3 examples of how you do optical cloaking in real life. The first one we look at is mirror and single prism. So in this context, we can use something like a mirror. If you look at the viewer's perspective, which would be us, if we didn't have any mirrors there, you could see the bunny with no problems. But instead, what's happening is the mirrors are bouncing the light around the rabbit so that you can't see it. So in the top right, you can see the gift of the kid. The older kid is actually where the light source would be, and the little kid would be, from our perspective, the rabbit. So as the light is moving towards him, the light's being bounced around by a series of mirrors, which is why we can't see the little kid's feet, but we can see the older kid's feet. Now you can see there's limits to this though. So if you look at the bottom image where you can see the trash can, the chair, you can see that where the trash can lines up, it's completely mismatched, as well as the wood in the background. So in this context, parallax is a big deal because if your angle's not good on it, then it's going to be completely exposed as to what's actually happening. The next case is all lens-based. So the way this is working is that we're tightening and expanding light. In this case, you can see that there's these 3 different sections. It actually doesn't matter, but there's a preferred location for this. So if you look at the first section and we're zoomed in, you can see that the light gets super tight right there. And what happens is you can stick your hand in like this guy is, and as long as you don't obstruct the light, your hand will appear invisible wherever you look in at the lens from, because all the light is being contracted into one location, so that so long as you don't obstruct it, your hand won't appear visible. But if you do obstruct it though, your hand's gonna, well, it's kind of weird because when you see it, it's not gonna appear like your hand normally would. It's actually become like just a big black splotch because then all the light's bouncing in random directions. It's gonna look very strange. And then the last one is optical cloaking. This doesn't actually exist in real life yet, or at least not to the scale that you think it, that you probably would explain. But Alex brought up where you have cameras that are taking in an image on your front side and your back side. And then you also have a display that's showing what your back side's seeing, and on your back side, you have a display of what your front side's seeing, so that when someone looks at you, the image would appear to be just the other side of you. And if anyone's seen the horror movie The Invisible Man, that's how the guy turns invisible in it. But in real life, though, there's not really any practical application. Now, you could simulate this really poorly if you got something like 2 phones and you FaceTime each other, and you put one phone on your chest, and then you had another phone on the back side of you. You could look through the person, but again, that's not really convincing. So, and then also parallax is a big problem with Alex brought, because as the person changes the location, the suit would have to also be calculating your new perspective on it, which this technology is insane, so it's kind of far away.
Okay, so challenges, size thanks to cloak. So as we mentioned, and even in the carpet cloak right now, science has been able to cloak smaller objects, but when it comes to bigger objects, there's more light reflecting, so it's kind of harder to create a certain cloak that, can cover a large object. And then static versus moving objects, like the kid that was standing behind the mirrors, that's easy to cloak because he's not moving, so then we have all these mirrors lined up. But say if he wanted to move, then that's not possible, because if the kid moved to the left or right, then he would be out of the frame of the mirrors. So for example, this is being used kind of in the military, where if you have soldiers in battle, but not necessarily moving, just stationed. And then other challenges: ability of magnetic response to be equal to electrical response, requiring phase velocity to be greater than the speed of light, limited to given materials, which is the big one. Oh, 1 minute. Okay, and
Then our last slide. So usually the fictional examples of what we can do. Harry Potter and like Fantastic Four are like completely nonsense because you get like magic and superpowers. So that's obviously not happening anytime soon. But you really get something like Star Trek. You know, it's in the year 2364. So if you're patient enough, maybe you'll get to see it. Any questions?
Was the real or the passive cloaking? You said it was real.
Yeah, that
The,
one
like,
image.
big code?
Yeah, the one image here. That is a real picture, from my understanding.
Which do you think are going to be the first applications for this?
So one of the things that we didn't really touch on is optical cloaking doesn't necessarily need to be visible spectrum. If you have, let's say, a boat out on the water and somebody's trying to see with infrared, you can try and spoof them using IR, which is a non-visible spectrum. So my guess, probably military. If I have a something somewhere and I don't want people to find it, and I know what they're trying to look for it with, then I can try and hide it from those specific wavelengths.
Yeah, or even like aircraft.
That too.
Yeah, I'll add that that's actually an active area of research. I think on your first slide you showed the whole electromagnetic spectrum. That a lot of those are detected using radar, which are longer wavelengths. Sorry, I forget this. But that's just light longer wavelengths, and they're looking at actual cloaking devices for ships and aircraft. Advanced coatings and things to avoid detection, which is pretty cool. Any other questions for the group?
Would you say an octopus is cloaking itself?
That's camouflage.
Camouflage?
Not in the same way that this is. It's not bending light around it, but it is
Yeah.
trying to just make itself look like it is the environment.
Sounds good. Lots of good theory in the beginning. There's a lot of it, so you need to worry about cloaks, not only index of refraction, but like you said, polarization, permeability, all
Yeah.
those other variables, line of sight, dealing with parallax. So it's super challenging, but it's kind of I don't call it the holy grail for opticians, but it's a really big challenge that people are looking to have solutions to, not just for magic tricks. Make it better. But thank you. That was great.